So let's finish up the last few topics in section 1.5. Okay, next up is Theorem 1.12, conditions for A inverse to exist. We'll have, this ain't the end of it, a bunch of conditions equivalent to the invertibility of a matrix. Now, one way to remember these is to think how you find the inverse of a matrix. As we just saw, you take matrix A, augment it with the identity matrix, row reduce A to the identity, and while that happens, on the right-hand side, the identity matrix turns into the matrix A inverse, if indeed A is invertible. So if nothing goes wrong, that's how you find the inverse. With that in mind, we get the following. The following conditions are equivalent. Of course, talking inverse, we have to be speaking of square matrices. A is invertible is equivalent to the following. A is row equivalent to the identity. Sure, that's how you find the identity. You take A, augment it with the identity, and row reduce A until it becomes the identity. When it does, you found the inverse by what happened to the identity in that augmented matrix. And if that result doesn't work, then there is no inverse, as we've commented earlier. So the fact that 1 and 2 are equivalent should make total sense. AX equals B has a solution for every B in Rn in this case. Sure, if A is invertible, then that solution is given by, if you like, X equals A inverse B. If A is not invertible, we saw in the past an explicit vector B, for which there was no solution of AX equals B. Previous section, I think. So this ties in with invertibility and results in the previous section. Matrix A, can be expressed as a product of elementary matrices. All right, what's up with that? We're going to look at that a little bit more here in an example. If A is a product of elementary matrices, we could find the inverse of each of those matrices in that product. And by the way, inverses of elementary matrices are easy. It's the first kind of matrices we found inverses of. And multiply A by a product of the inverses of these elementary matrices and effectively reduce A down to the identity. Refer to part 2. That means A is row equivalent to the identity. We're just using the inverses in a sense of the elementary row operations that reduce A down to the identity in determining these elementary matrices. More of that in a second. There's nothing but elementary matrices in A as a product, then they're related to the row operations that will reduce A down to the identity. More of that shortly. How they're related is a little involving inverses. Part 5, the span of the column vectors of A is Rn. We met that in the past as well, previous section, I think. Story here being the span of the column vectors. Hey, when you look at AX, that gives you a linear combination of the columns of matrix A, right? Right. It's note 1.3.A. I wouldn't remember that if we didn't use note 1.3.A so often. When you take a product, matrix A times vector X, that yields a linear combination of the columns of matrix A with coefficients given by the components of vector X. One of the first observations we made when we defined matrix multiplication. All right, well, saying AX equals B has a solution for every B in Rn, is saying anything in Rn, call it matrix B, can be written as a linear combination of the columns of A. Hey, the span of the columns of A, that's the column space of A. So the span of the column vectors of A, or, so I jumped the gun a little bit, we'll call that column space here shortly, but the span of the column vectors of A, the collection of all linear combinations of the columns of matrix A, and we can produce those linear combinations by varying vector X, can be made to be anything in Rn. In other words, the span of the column vectors of A is all of Rn. So part 3 and part 5 really say precisely the same thing in different terminology, arguably different settings. Up here, we're talking systems of equations, and down here, we're talking spans of column vectors. Well, when you talk systems of equations of this form, you're talking about a linear combination of columns. So different terminology, exact same concept. So there's some conditions on the invertibility of a matrix. A is invertible if and only if any one of these 2 through 5 things hold. We're not done. We'll add to that list over the remainder of the course and give additional things that are equivalent to a square matrix A being invertible. All right, part 4 dealt with A as a product of elementary matrices. Okay, A, say, is a left to right product of the inverses of the elementary matrices corresponding to the successive row operations that reduce A to I. So that's where I said determined by. Yeah, it's a little involved. Let's do an example to illustrate what's going on. The thing is, we've got matrix A, we've got a bunch of elementary matrices, we've got the identity matrix. Somewhere in there is the inverse of matrix A if it's invertible. And the inverse of matrix A is related to the inverses of a bunch of elementary matrices. All right, so let's see what we got. Here's a matrix, 2 by 2 matrix, 3, 6, 3, 8, says express the inverse of A as a product of elementary matrices. All right, I tell you what, let's write both A and A inverse as a product of elementary matrices to get straight this comment above about inverses and elementary matrices. Okay, well, here's the plan. And we didn't have some grand formula or theorem relating this. We just know that elementary row operations are accomplished by multiplication on the left by appropriate elementary matrices. Okay, elementary row operations are performed by multiplication by elementary matrices. With that in mind, that's the central idea. Let's see what happens. Let's take matrix A, 3, 6, 3, 8, and reduce. So we're going for reducing what's left of the augmentation bar down to the identity. Looks like it doesn't take long. Oh, and whatever happens on the right will produce the inverse of matrix A. It looks like it works. A is invertible. So let's see how we'll do it. Okay, so I'm looking at 3, 6, 3, 8. I want to get a 0 there. We're going for reduced row echelon form. You might say, well, don't you want to get the 1 here first? Sure, go ahead and do that if you like. We'll divide the first row by 3. No problem, no problem. Geez, I get a 1/3 there. Let's put that off. It looks like we'll end up with thirds and halves somewhere along the lines. But anyhow, let's not divide by 3. Not wrong. Just let's push the fractions as far back as we can. So let's use the 3 to eliminate the 3. So we'll take row 2 and subtract row 1. All right, 3 minus 3, 0. 8 minus 6, 2, 0 minus 1, negative 1, and so forth. Okay, next, we've got a pivot. We're not done with the first row. We're going for reduced row echelon form, but we do have a pivot down and to the right. A pivot, this matrix, I'm really concerned with the 2 by 2 matrix to the left of the partition. This matrix is in row echelon form. So by the way, it is invertible. We just got to finish the process. So let's take, either take this 2 and divide by 2. No, let's not do that. That'll introduce fractions. Let's take this 2 and eliminate that 6. We'll take row 1 and subtract 3 times row 2. Row 1, subtract 3 times row 2. Okay. The 0 here doesn't mess up that pivot there. 6 minus 3 times 2, 6 minus 6 is 0. And the additional arithmetic, I leave it to you to go through that more slowly. Notes are posted, you know the story. Okay, now we've got this almost in reduced row echelon form. Pivot and zeros above and below, pivot and zeros above and below, down and to the right. Only thing we need to do is make these pivots 1 to get this in reduced row echelon form. Okay, so now we'll have to divide the first row by 3 and the second row by 2. Let's do those separately because remember, I want to reflect each of these 4 elementary row operations with an elementary matrix. So first we'll divide row 2 by 2. That'll get us a 1 there, and some 1/2 and -1/2. And take row 1 and divide it by 3. Ta-da! Reduced row echelon form. It's the identity. Matrix is invertible. There's its inverse. It's got some fractions in it, which tends to happen in inverse matrices. Okay, so question was, express the inverse of A as a product of elementary matrices. Here's the sequence, first, second, third, fourth, of elementary row operations that reduce matrix A down to the identity. So if we took matrix A and did this first, we could represent that by multiplication on the left by an elementary matrix. Did this second, we could do that by multiplication by an elementary matrix on the left. And this, elementary matrices on the left. Order matter? Probably. Actually, I guess I could have interchanged these last two. But in general, order matters, so I'll be consistent and keep the same order on the elementary matrices that we had on the 4 elementary row operations. So next, let's represent, let's try to shrink it so I can see it all at once. Let's represent those 4 elementary row operations by elementary matrices. First, row 2 went to row 2 minus row 1. Take a 2 by 2 identity matrix and do that. Take row 2, subtract row 1. Produces a -1 here. Looking at this matrix, we'll call this E sub 1. Secondly, we took row 1 and subtracted 3 times row 2. Take a 2 by 2 identity matrix, subtract 3 times row 2 from row 1. It'll introduce a -3 right there. We divided row 2 by 2 and then divided row 3 by 3. Divide row 2 by 2, divide row 1 by 3. Okay, and how would you undo each of these? So here are the matrices that represent the 4 binary operations we just did. What about their inverses? How would you undo subtracting row 1 from row 2? By adding row 1 to row 2. How would you undo subtracting 3 times row 2 from row 1? By adding 3 times row 2 to row 1. Undo dividing by 2, multiply by 2. Undo dividing by 3, multiply by 3. And indeed, these 4 matrices are the inverses of these 4 matrices. All right, so what we have is, if we took matrix A and first multiplied it on the left by E sub 1, that accomplishes the first elementary row operation. What is E sub 1 times A? Should be this. We take this and multiply by E sub 2. E sub 2 performs this elementary row operation. Should be this. Multiply by E sub 3, get this. Multiply it by E sub 4, get this. On the left, in order. In order, E sub 1 is first, right? You had to multiply on the left. That was the rules. Multiply on the right, something totally different happens. Column operations, and we're not going there. Yeah, E sub 1 reaches A first. And then E sub 2 reaches the result of that. And then E sub 3 reaches the result of that. And finally, E sub 4 reaches the result of the first 3. And we get the identity out. We row reduced A to the identity. So, what was the question? Let's read the question again. Express the inverse of A as a product of elementary matrices. So how are we doing? You know, here's stuff we've multiplied A by on the left to get the identity. A is a square matrix. If we multiply it on the right, if we interchange the order, I bet you we get the same thing. It'd be the interchanging the order of the whole thing. But yeah, we found an inverse of matrix A. A inverse must be this highlighted stuff. It's E4 times E3 times E2 times E1. The product is performed in this order. I can't reverse the order. I didn't talk about reversing order up here. I said do this multiplication first, and then this multiplication, and then this, and then this. Associativity says you can do it. Performing any operations you want first, you just got to keep the order the same. So it must be this is the inverse of A. So there's A inverse written as a product of elementary matrices. If you wanted to write A itself as a product of elementary matrices, we could take the inverse of this, or I could take each of these and effectively, I talk like this in a numbers setting, move E4 to the other side. Well, what you do is you multiply both sides on the left by E sub 4. That'll eliminate this. It'll produce an identity matrix, which you can drop. And over here, we'll get E sub 4 inverse times the identity matrix. So we'll just pick up an E sub 4 inverse on the right-hand side. Next, take the E sub 3. Multiply both sides by E sub 3 inverse. You pick it up on the other side and so forth. So we could effectively move these elementary matrices to the other side. We'd have to deal from the left. First, E sub 4 goes over. From the left, E sub 3 goes over. From the left, E sub 2 goes over. So we'll get these written out on the other side, E4 inverse, E3 inverse, E2 inverse, E1 inverse. The order's backwards from what it was. You've seen this before. You've seen it when we talk just straight up inverses of a product, and we could apply that result as well. So there's A written as a product of elementary matrices, and there's A inverse written as a product of elementary matrices. We've more than answered their question. In a box, there's the answer to their question. But up there in the theorem, it said something about writing A as a product of elementary matrices. Here it is. It also said something about inverses. The note before this question said, let's read it again and make more sense now. A is the left to right product of the inverses of the elementary matrices corresponding to successive row operations that reduce A to I. The successive row operations are these four things right here. The elementary matrices corresponding to them are E1 through E sub 4. And the word inverse was in there. The inverses are E1 inverse through E4 inverse. So that's what that means. We can write A as, they said, left to right product. It's easier to write out a little bit of the manipulation so you can see it more cleanly, in my humble opinion. But we get A as a product of these elementary matrices, and A inverse is a product of these elementary matrices. Because we're dealing with reducing A and then talking about A, we end up with inverses when we write A as a product of elementary matrices. The inverses of the elementary matrices corresponding to the elementary row operations as above. Okay, we get too hung up on the words, but the concept, and the only concept here is elementary row operations can be represented by multiplication on the left by elementary matrices. That concept makes this whole thing tick. By the way, if I wanted to explain why that technique above for finding the inverse of a matrix works, cleanest way to explain it is probably in terms of elementary matrices. We explained it actually in terms of solving a bunch of systems of equations. Elementary matrices, in my humble opinion, is a little cleaner. And a couple of examples. So let's hop over to the supplemental notes. Let's try to hop over to the supplemental notes. Here we go. Okay, question says, prove that if A is an invertible n by n matrix, then A transpose is invertible, and describe the inverse of A transpose in the terms of the inverse of A. All right, so A is invertible, find A transpose inverse. Okay, one thing, when we transpose a product, we get the product of the transposes, but in the reverse order. That was some result concerning transposes and products back in section 1.3. properties of the transpose operator, I guess. Okay, just as an observation, because we're going to need it. All right. Since A is invertible, then we know A times A inverse equals A inverse times A equals I. Really, there exists a matrix denoted A inverse where this equation holds. It's the very definition of invertible and inverse matrix. All right, so let's take AA inverse transpose, and let's take A inverse A transpose. So I'm really transposing each of the three things in this equation. Transpose the first, transpose the second, transpose the identity matrix. Well, the identity matrix is symmetric, so it equals its own transpose. The rows are what? You know, the rows of the identity matrix are the standard basis vectors of Rn. So is its columns. So the rows and columns are the same. So I transpose equals I itself. The identity symmetry is what gives us that technically. Okay, so let's see. Let's manipulate both of these with this first observation. A inverse transpose. So let's see, I'd go up here. I've got A for A, and I'd replace B with A inverse to match up the symbols. And by this formula, we'd get A inverse transpose would equal, let's see, so we get B transpose, that'd be A inverse transpose, and we get A transpose second. If that's too much for you, then forget trying to do the substitution with B. I transpose both of these and reverse the orders. So we'll get A inverse transpose, but that'll come first, and A transpose, but that'll come second. From this one, we'll get A inverse transpose, but that'll come second, and A transpose, but that'll come first. So the order is reversed on the inside, so when we do the transpose, we've still got a reversal on the orders. Transpose of the identity is the identity itself, it's just observed. So we get A inverse transpose, A transpose equals A transpose, A inverse transpose equals the identity. We just found the thing we were looking for. We were looking for, let me speak of it maybe more verbally than symbolically. We were looking for the inverse of A transpose. That'd be a matrix that we would multiply A transpose by to get the identity on both sides. A transpose is multiplied on one side by this thing, gives you the identity. A transpose is multiplied on the other side by this thing, gives the identity. This thing is the inverse of A transpose. The inverse of A transpose is this thing, A inverse transpose, or more symbolically, the inverse of A transpose inverse, is A inverse transpose, which is kind of cute. These transpose and inverse things are interchangeable in some sense, interchangeable in this sense. Oh, none of this making any sense at all unless we deal with square matrices. Transposes I can talk about without square matrices, but not the inverses. So we need the square matrix stuff. So A transpose inverse is A inverse transpose. I like it for one thing. The argument was really simple. Let's do another one. Okay, a new idea here. You may well encounter this idea in the future. If you take our Introduction to Modern Algebra class, idempotent is an idea that will pop up again. If you do a bit more of this matrix theory stuff, you're likely to see this idempotent idea again as well. Definition here, they snuck in this question. Square matrix A is said to be idempotent if A squared equals A itself. So you multiply the matrix by itself, you get the matrix back. Quick, give me an idempotent matrix, the identity. Give an example of an idempotent matrix other than the identity. Well, in the zero matrix. So those are idempotent. Find another one. Well, the thing to do really is to kind of rip off the behavior of the identity. Now, I know there's an infinite number of ways of doing this. Here's one way, and it is kind of an open-ended question. Just give an example. Let's try this. Let's take a 3x3 identity matrix and just put a 0. Change that 1 in the identity matrix to a 0 here. Let's check the multiplication. the first and third rows are still going to behave in an identity way. Second row, all zeros, that's just going to swamp everything out and produce nothing but zeros when we do the matrix product. And indeed, first row, first column, nice things. Third row, first column, second column, third column, nice things. Second row, first, second, or third column, 0, 0, and 0, which is what we started with. So there's an example of a somewhat more interesting idempotent matrix. Now you ought to have a clue as to how to make up a whole bunch of these things. Yeah, I'd take an identity matrix and change some of the zeros along the diagonal. Sorry, some of the ones along the diagonal, change to zeros from an identity matrix, and it'll work similarly. Part B says, prove that if a matrix is both idempotent and invertible, then it must be the identity. The only idempotent invertible matrix is the identity, is an alternate way of saying it. Okay, take a matrix A. Suppose it is idempotent, that is A squared equals A. That's what idempotent means. And A inverse exists. It's invertible. Okay, consider A inverse A squared. Hey, A squared equals A, that's the idempotent part, so that's the same as A inverse times A. Also, A inverse A squared, that we can rewrite by grouping the A inverse with the first A in that product, using associativity here, as A inverse times A, and there's the second A. So we've taken this expression, written it like this, taken this expression, we can factor, we can use associativity, and express that same term as A inverse A times A. All right, so that'll also equal A inverse A, so we've got equalities here. Hey, A inverse A, that's the identity. So we've got the identity times A on the left. On the right, we've got A inverse A. Well, that's the identity. So we've got A equals the identity. Excellent little problem. I don't know, good bonus question on the test. Maybe. It's hard to get partial credit on it. It happens so fast. Neat thing, all you use is what you're given. The definition of idempotent and the definition of invertible. And that takes care of section 1.5. So we'll move on, wrap up the material we're probably covering in class from chapter 1 by doing section 1.6. I'll see you there.